Okay, so we're going to have a look here at chapter 3 of statistics, which is called representations of data. So basic idea here is we're going to show data instead of just sort of calculating things. We're going to show it, present it in a number of different ways, and we can mix this together with the skills from chapter 2, such as standard deviation, estimated means, etc. The main skills are here. So Boxplots and Outliers first. So if you've done some GCSE statistics or just regular GCSE maths, you would have seen Boxplots a little bit before. And these over here, these would be the outliers. You should be at least a little bit familiar with cumulative frequency diagrams. So cumulative frequency, this is when you're keeping a running total, when you're adding the frequency together. So you see here, this number only ever goes up. And the shape of this sort of tells us about how frequencies are distributed. And this can even be used to create a box plot. And then finally, probably the more challenging part of this topic is histograms, which is because there are some more challenging questions generally anyway for this. But one new thing in particular is the use of scale factors with histograms. So to start with, we should just remember what a box plot is. And a box plot shows 5 main pieces of information. The minimum, in other words, the smallest piece of data, okay, which is represented by a vertical line. The lower quartile, so this is the position in, or in other words, a quarter n. For exact ways to calculate this, we need to go back to chapter 2 and check the rules on that. But we're more interested now in just sketching with that value. So we draw a line from the minimum, and then another vertical line at the lower quartile. The median, which can be found in a similar way, so half n is 17, with another vertical line. The upper quartile, which is the 3/4 in position, okay, so the data that you have 75% of the way in, is also sketched this way. And then we draw sort of a box around this, which is where box plot comes from. Finally, we have another whisker on the right-hand side. So sometimes it's called a box and whisker diagram. And the general idea here is that each section between the vertical lines represents 25% of pieces of information, the data. So for example, we can see that between 15 and 17, 25% of the information is very, very close together here, very, very consistent, whereas it's a lot more spread out here. And that might just be the way that the data is, or perhaps it could be due to something like an outlier. And again, these other sections are made up of 25% each. So for example, I could say that 75% of the data, okay, has a value of 22 or less. Yeah, and this is something sometimes that you're asked about, which is using the 25% together. We also talk about interquartile range, you remember from chapter 2, and that's shown by this middle 50%, 25% to the left of the median, 25% to the right. Okay, so from 15 to 22. So this here, this would be 7. And the range, well, the range is a wider measurement. It takes into account the minimum and the maximum. So this here would be 24. Some quick questions just to check we understand what's going on with the box plot. So the right box represents more people than the left box. Well, this is false. Okay, they represent the same number because they represent the same percentage of people. The ages are more spread out above the median. So the median is here. So above the median, the ages are more spread out. So, you know, this is true. Without putting any numbers to any data, yeah, we could say that there's a positive skew going on here, certainly. Outliers then. So outliers, you'll probably be fairly familiar that an outlier is sort of an extreme value of data that you know, doesn't really follow the general pattern. So We can call an outlier an extreme value, but often there's actually a definition, okay, a robust definition that's often used, is that an outlier is 1.5 multiplied by the interquartile range added on from the upper quartile or taken away from the lower quartile. So this plus sort of the interquartile range times 1.5, or this minus, let's write this the other way around, minus 1.5 times the interquartile range. Sometimes this value, sometimes this boundary, I should say instead, you might find sometimes this will cause you to exclude values. Sometimes it makes no difference. And it's the same over here. Sometimes this will affect things, other times it won't. If we use above here to sort of illustrate it, so if this is the upper quartile, and if this is the IQR times 1.5, we would say that this is our sort of region where anything to the right of the region would be an outlier. If we compare to the maximum here, we can say it's unaffected. Over here, okay, we can see that this would be the critical region, and actually we have at least one value. We don't know exactly, but we know at least that the minimum would be an outlier. And typically we would replace that with a cross, okay? And depending on the question, we might illustrate the new boundary according to this, or we may be given a new number to replace the minimum with a new minimum. So let's do a couple of quick questions. So the diameters of 11 coins are here below. Determine the quartiles and hence any outliers. So calculating the quartiles, this uses chapter 2 knowledge. So you should revise this if you're unclear. This is our lower quartile. This is our upper quartile here. The interquartile range can be found by their difference. And then 1.5 times this can be taken away from the lower quartile, and 1.5 times this can be added on to the upper quartile. And this is your region, okay? So any regions that are less than this one here, and any values that are more than this one here would be considered outliers. Every number here is 2 point something or above. So this part here, this does not affect anything. However, 3.95 means that we have 2 outliers here in the list. Another example, the lengths of giant African land snails, blah, 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 blah. We've got our numbers here. Calculate the mean and standard deviation. Well, mean, sigma x, divided by n is 12, so we can fairly easily calculate the mean. Standard deviation as well, ms, m. So the mean of the squares minus the square of the mean. The mean you've just calculated in the first part. This part here, you need to use the information. You can calculate these numbers here. Don't forget to square root for standard deviation. So part A is really chapter 2. But why is this question coming up here? Because we can use outliers with this. So you're being given an alternative definition for an outlier. Here it says an outlier is plus or minus 2 standard deviations from the mean. Well, the mean is 21. The standard deviation is 3.83. So according to this new definition, which we have been given, if we have 21 plus or minus 3.83, this will give us, in fact, let's say 3.83 times 2, because it's 2 standard deviations. This will give us our new boundaries, okay? And then we will check, especially the lowest, the minimum and the maximum, we will check if there's any outliers. So we see our new boundaries are 13.34, so the lower end will be unaffected because 17 fits within that. At the higher end, we've got 28.66, so 32 lies outside the region that we consider not to have an outlier, it is an outlier. A couple of questions, a couple of two-part questions there. So just have a quick go at these here to see that you've got the idea. So pause the video. Okay, and just check your answers with this one here. So should be able to get these values here. Okay, and the focus really is on outliers at the moment. Okay, something else you should be confident to do, and a required skill, is sometimes you need to draw a box plot. So let's have a look here and understand why we are being given sort of two sets of values for minimum and maximum here. So why are we being given this? Well, if we use the information, the lower quartile and the upper quartile gives us the interquartile range of 6. And if we use our standard sort of definition of 1.5 times the interquartile range, we could introduce boundaries, and we could say anything greater than 23, anything less than -1 would be an outlier. Why is this useful to give this information at the top? Well, we see that 27 lies outside, so we're being given this value here, so we could replace the maximum with this new value here. The smallest values, there's no need, there's no change. So if we wanted to draw a box plot here, we have two choices. So the median, the lower quartile, the upper quartile, and the minimum should all appear as this. What you have on the right-hand side is you have two different ways that you may construct the diagram. The first one, well, either way, we're going to put a cross down for 27 to show that that information was recorded but is considered an outlier. And then we could choose to redraw the maximum at 21. This is one choice. Or, and or is important here, you can't do both, or you might opt to, or if you're asked to do so, you could draw the new maximum as going up to 23, because this is the boundary above which a value is considered an outlier. So basic skills being tested here, first of all, drawing the box plot, but how to handle redrawing it after an outlier. And there's a test your understanding question on the screen. Well, here I'd like you to pause the video and to have a go at the question. So I'm assuming you have done that and should get the answer on the screen. Notice the use of either here. Okay, and the answer to this other part. A final skill, and I'll keep this very brief, is comparing box plots. If you need more practice on this, or any part from 3A, B, and C, I would recommend you go on Hegarty Maths. There's plenty of practice, including 3D as well, for the more basic version of these questions. Comparing distributions on box plots, okay, generally you want to go for the two keywords in chapter 2, which is location and spread. So if we're talking about location, you might use median. Median is sort of the average, so a comparison of the median points. And then spread, we're talking about interquartile range, which is the width of the box, or you may wish to talk about range, which is from the minimum to the maximum for each alternatively. To be safe, I would talk about interquartile range, and median is then more useful, I think, and more important. It's location and spread, and I would try to contextualize the answer a little bit, as well as using the key language that is in bold. And that will take you to 3A and 3B, and you should have a good go at these questions, especially as there's not many of them there.